So welcome to this talk. I will, in the half hour coming or 20 minutes coming, try to introduce you to imec, if you don't know imec. And if you know imec, maybe tell you about some things you might be less known about imec, some technologies under development. And I'll try also to make you think of power systems maybe slightly differently than you typically do. But first, let's introduce imec. So imec is a 41-year young research center. We're in partnership with many companies and research centers leading or driving the roadmap of microchip since these times. We are headquartered in Leuven, Belgium, at the heart of Europe. And we are in a network of, at the heart of the network of universities from Flanders, ranging from Kortrijk, Antwerp, through Brussels, Ghent, and Hasselt. We're also present globally. So we have obviously our headquarters in Belgium there. We have very strong presence in the Netherlands, and I wanted to apologize to Eelco, the previous speaker. I might be late submitting our proposal, but we are very happy to have Photon Delta as a partner. So we have also a presence in UK for design, in Italy, and also in Germany for design towards automotive. We are also setting up currently a new fab in Spain, 300mm capable. And we have further collaboration throughout US, on the West Coast first, Berkeley, San Jose, but also working on 2D materials with Purdue University, automotive in Michigan, cryogenic electronics with Florida, and have a new hub in Boston to interface with MIT and Harvard around life science, but also quantum information theory. We have a presence in Asia, but representation only at this point in time with Korea, Japan, India, and of course, Taiwan here, where we are very happy to be again. We are very diverse. We have 6,000 employees throughout. Our talent is our main value, we say, and we have more than 100 nationalities represented, so we are really somehow an image of the world, we think at least. We work with more than 600 partners in the full ecosystem, from material and tool suppliers through design houses, IDFs, foundries, fabless, fablights, and so on, companies going towards system partners too. All of these efforts mainly revolve around $3.5 billion or euros installed capabilities in Leuven, with 12,000 square meters of clean room, state-of-the-art 200mm, 300mm, and also a lab area, which is very important. We are now expanding to 6,000 square meters, with 6,000 more square meters, clean room 300mm in the headquarters through the European Chips Act and local funding, with a level of 2.5 billion for this investment. And the Nano IC program that Europe paid to indeed install these new facilities is to give more access to ultra-scaled nodes down to and below 2 nanometers mainly, but also to diversify the use of these platforms and these capabilities towards more applications. And definitely to lower the threshold for European but also associated partners to access these technologies. So we're very proud of this development. Now, I'm not so much related to the scaling, but to the diversification of output of these capabilities. And so we provide this diversification towards health, automotive, agri-food, energy, consumer industry, but also aerospace and security fields of applications these days. And I will, for this presentation, pick one example just as a way to structure the story that I want to bring you, and that's the one about automotive and sustained affordable mobility. So we cannot deny that the trend and the move towards electrical vehicle is ongoing and very successful, and that all these new vehicles revolve around an e-drivetrain and battery management systems. And this is what I will want to tell you about. And these battery management systems have to make sure that they deliver power to all these sensors that will enable autonomous driving of the future, of the current, but definitely of the future, with multi-spectral cameras, different LiDAR, different radars, but also support in-cabin monitoring for usage, health and safety, and feed all this data to zonal gateway that will move all the information to a central compute unit with high-performance computing probably required. All of that use quite a lot of power, and this is what we're here to talk about today. So So I would like you to keep that image in mind while I'm going through my presentation. That is that of a battery pack with a power management unit hanging to that one. So we are working towards this green energy transition, and the question we are wondering at imec very often is what can electronics or microelectronics or nanoelectronics do for this transition? And I'll take you through some of the topics that we tackle at imec that might be less known. The first one is that we're working on generation of electricity or power, and that is through photovoltaics. So in that sense, we are working on perovskite devices and tandem solar cells, and also new technique to produce them and to embed them in buildings using these transparencies while maintaining quite large collection efficiency. Working on interconnection technologies and also on energy yield modeling for these solar systems. Now that's a little bit about the development and the research, but beyond that, we are very conscious that we have to work on the MRL while you're tackling the TRL. So that's why we have our own module integration and characterization line in Energieville in the north of Leuven, where we are manufacturing test devices and stressing those to replicate what would be a production line full-blown for high volume. Next to that, we are working on what we call power to molecule. That means that you have power, but you need to store these in one way or another in a more easy to manage form factor or material. For example, we're working on hydrolysis of water, very efficient to produce clean hydrogen, but also in general to the theme of catalysis. We are working on catalysis to capture carbon, but also we're working towards a multi-stage thermocatalysis where we capture carbon, bring these through different stages of catalysis until having fuel as output. To do that, we are working on the semiconductor or the manufacturing facilities linked to semiconductor manufacturing. And for example, we're working on these nanomesh, extremely porous structures that we are developing by pure sequential chemistry steps, where we can grow vertically, then laterally, and interweave then these meshes with nano resolution in order to produce materials with very large porosity, very large surface area, with low resistance, so that you have a very efficient electrode, for example, for hydrolysis, but in general for catalysis. We're working further on nanocomposite electrolyte and membranes, engineering interfaces within these systems for gas or liquid proper interaction. And again, we are producing demonstrators. We have cell integration and assembly lines at Energieville so that we can produce demonstrators that mimic what would be produced in an actual facility and test and stress these type of outputs to make sure again that these technologies that we develop have a potential impact in the field. And this brings me to the battery topic. In batteries, let's say we have had many different developments. Some of them are brought to the public right now through two ventures, Solitos and Hive, that are bringing some of our developments out. But basically we have the same approach. We're working on different interfaces, different metallurgies, and different structure based on 3D, easy to produce 3D features for solid state or liquid type of batteries, roll-to-roll production. And you see that we have also here a battery pilot line where we can produce demonstrator, stress test those within our facilities. That takes you very far from the ultra-scaled nano IC that I mentioned at the start. Nevertheless, very important. So that was about generation and storage, and now I'll move to the conversion problem, because this energy is not readily usable as is, and we need to shape or to tune the voltage of these levels that we produce with the solar, for example. And in that perspective, imec has very long back decided to develop a power GaN program. Some of you might know about that. It started about 25 years back when we worked on gallium nitride and started developing the gallium nitride growth on silicon. We picked gallium nitride because silicium carbide is known to be clearly outcompeting silicium, but gallium nitride has a perspective of clearly outcompeting, also outperforming carbide. And the next one that might do is diamond, but diamond production is very complicated, so we decided gallium nitride is probably the way to go. We're not the only ones there, but that's what we did 25 years back. So we developed first gallium nitride on silicon in 6-inch in our facilities, moved then further towards 8-inch first, and then had our first E-mode transistor with 200 volt around 2016. Moved then to 650 volts, and then had a full E-mode platform with 100, 200, 650 volts around 2018. I'll tell you more about the next step in the following slides, but it's very important to clearly make the difference between gallium nitride on silicon and gallium nitride IC that will show up in the next slide. We moved then in 2019 to 8-inch gallium nitride IC with 200 volt PDK available for designing complex circuitry. The PDK becomes very important when you talk about ICs. Then we moved to 650 volt gallium nitride IC PDK, and for a few years we are working on development of 1200 or 1200 volt gallium nitride on SOI, but also on chromis substrate tech. Nowadays we have bidirectional switches, we have also E-mode device, lateral, vertical, we'll talk about that. And we're currently, you see on the top right, working on extremely low R-on. Further moving towards 300 millimeter, because that's the next frontier to some extent for production, and stabilizing the 1200 volt development that we had first on lateral HEMT, available now, and still researching or developing the vertical HEMT at this point in time. I could stop the presentation here, but because I have you, I will go on and detail some of these steps in the coming minutes. So you see that the program that we offer is stratified in 3 layers. I will start with the bottom one, which is the development that we started in the past years, moving towards 12-inch and 300 millimeter wafer, basically. So that is the deep layer of the program development for those partners that really we need and want to participate to their development. The second track is an exploratory track where we basically try out options. We develop a demonstrator and we try out different architecture, and that's where we start, for example, the exploration of novel substrate and devices. We move then to developing the baseline gallium nitride IC, still in exploratory mode before moving to the track 1 that I'll tell you more about later, and that's where we started the development for the 1200 volt devices, for example. And currently we are at the point where we have some 1200 volt device that perform, doesn't work fine, laterally and vertically still in development. The top track, the track 1, is the one where we mainly focus on industrialization and stabilization. That we stop the fancy developments, the tryouts, but we offer very stable, designable platforms where we develop PDK that we can offer to our partners for them to try out the technology before asking us, hopefully, for tech transfer. And here you can find back some of the development of track 2 in terms of lateral HEMT Gen 1, then Gen 2 with gallium nitride IC baseline development, the Gen 2 baseline GaN IC, and now we are moving towards a Gen 3 for that. So this is about the structure of the program that we developed, that we run right now. So if you focus on the top track, the one on stabilization, you see that we have currently 40 volts and 100 volts in the same AP developed on silicium, and that is, if you see at the bottom, available for technology transfer for interested parties. We are working further on the right to the slide on 200 volt and 650 volt technologies on silicium on the one hand side, but also for 650 on QST. And these 2 technologies are available for technology transfer. That means that we have stabilized it to the level that we feel comfortable porting these to some partners, and we have also PDK available for them to compare to what we did in-house, but also to offer them to their clients for design. And again, on the right-hand side, you see that for the 1200 volt, we have very good result, but we are not ready at this point for tech transfer, but this is what we expect to see in the coming year. A little bit of details of cross-section of what we do, because it's always nice to see a chip in this presentation, I would argue. So you see a cross-section of a device on the left, where you see our 400, 100 volt and 200 or 650 volt indicative cross-section. We have a fully working transistor there, and that's what we call the pure GaN on silicium platform. And on the right-hand side, we have a copper redistribution layer and repassivation capabilities for better interfacing and packaging enablement of these dies, basically. Now, what you can do with this is very nice. You can produce this type of demonstrator where you have a half bridge, which is composed of 2 chips, basically packaged separately, and you use a PCB, basically, for decoupling of the pins for these devices. It works very fine. You can do that. You can think of doing system in package to have even more compact embodiment for these systems, where you can fold and advance You can use advanced features for the bonding and multi-layer substrates to do that, very nice. But you still rely on a separate component and you add many more parasitics to this type of embodiments. So this is why we moved a few years back towards gallium nitride IC, and where we have there the real capabilities to produce an integrated circuit on this high-power gallium nitride platform. What does it mean? What is the thought process that led us there? So if you see here the principal cross-section for some of our devices, you see they look splendid, I have to say. I find them very nice. But if you see the way you would want to implement these together in a half bridge, you see that while you can design that thing on the left, you will have a parasitic link, which is the dashed red line there, between the source and drain there of these two devices. So you cannot implement that on the typical pure GaN on silicon as is. That is the reason why you cannot have integrated circuit with this type of stack. So you need to produce a slightly more complex stack to do that. You need to implement isolation between devices. You can do that laterally by having trenches added to your stack, but you will still have, of course, the bulk contact from device to device that is remaining. And this is why we moved all our GaN on silicium development towards gallium nitride on SOI, because we get the buried oxide for free, and then you can develop these isolated pockets or swimming pool, let's say, filled with each one of your HEMT separately without having leakage from voltage from one to the other. So if you have that, then basically you can define a library component that will work always the same way, no matter what device you put around it on your chip. And that's enabled then by that buried and trench isolation. So if you look back at the technology I showed you just before, what we have implemented is on the SOI version, on the silicium version of this platform, we moved them to SOI. And then we have, for these SOI flavor, at the bottom, PDK release for multi-project wafer. And we run shuttles for our partners to try out their design and to get to know the technology. What can you find is this PDK? You can find basically high voltage power HEMT. You have also low voltage HEMT for logics and analog. And you have also high ohmic, low ohmic resistance and back-end capacitors. In the exploration track, we are moving further with other additional devices, only for those 200 and 650 volt. We don't have PDK released yet, but we are moving towards implementing these new low voltage D-mode logics and analog, and also lateral high voltage and low voltage Schottky diodes with integrated also MIM capacitors. So what are the results that we produced in the past years around these technologies? You can see here, and that's through, these are public domain demonstrator that we report. You see here, for example, a half bridge on the bottom left without the GaN IC, and on the right side you can see that you have a fully packaged single die half bridge that is enabled there. What you can do also is that you can then also produce then 650 volt and 100 volt half bridge, but also include drivers and current temperature sensing involved in these ICs around. And you can also move towards even more complex circuitry that are all full in single die that you can see here mounted on PCB, courtesy of Thales France as a partner from this project. I told you about the performance boost that you can expect from having not parasitic or less parasitics, and I want you to see then what type of performance we can show with this gallium nitride IC. This is one simple example. In view of time, you see here work in collaboration with Kyoto Institute of Technology that participated to one of those 200 volt GaN IC MPW shuttle. You see that you can have then MIM capacitor on chip that show 44% reduction in rise time and a fall time for the driving of these HEMT devices, basically. That's very simple. And also, as a courtesy of Mindset, we can show you the type of circuitry that people implement then on a GaN IC, power GaN IC technologies, where you have here half bridges, but you have also quite a lot of area deliberated to pull up pre-driver and drivers, as well as pull down pre-driver and drivers, and even input logic to those chips here. So 30% is gate drive, which is quite astonishing, and this simplifies a lot of the system development that you can produce in this approach. So to conclude on that precise topic, I would say that we have process design kit and MPW shuttles that we offer for willing partners, and we want to remind you that these technologies are so stabilized and ready for tech transfer if you are interested in that. That brings me almost in time to my third topic. That is the one following the previous and related to the fact that you need some additional features around a battery management system. It's very nice to have these batteries, these converters, and all these marvelous systems, but you need to be able to assess the health and monitor, let's say, the working principle or the working function, let's say, of your battery pack and overall system. And to do that, there is a known move towards contactless sensing so that you do not have galvanic contact to these power units, but you rely on magnetic field sensing for imaging or deriving the health of your system. Imagine you can measure in multi-points around that system the 3D direction and also the amplitude of the magnetic field. You can inverse the problem in principle and derive the current distribution in the pack. And if you don't want to do that inversion, at least you can derive when there is a drift in your system, an alteration of the performance, and then decide to take action. To do that, you need to have advanced magnetic field sensors and magnetometers. And we see throughout the years a change from Hall effect sensors up to tunnel magnetoresistive sensors. And these are seen as the emergence of quantum sensing for some. And TMR is known to have exquisite power consumption, very good form factor, field sensitivity, dynamic range resolution, and temperature performance. So you can find all of that as information online. So that's a very nice technology to develop for magnetic field sensing, but it's not a very simple technology to develop, in fact. In principle, you rely on stack of ferromagnetic materials with a very thin barrier layer or insulating layer in between, and the tunneling throughout will be depending on the parallel or anti-parallel state of the magnetization of these two layers. The bottom one is pinned, so it doesn't change. The top one can flip depending on the magnetic field that is applied to the system. Scattering of the electron through this top layer will relies in the fact that the tunneling is enhanced when the polarization are parallel, in fact. That's the story. Then the reality is a bit more complex because the actual stacks that you need to develop are much more complex and using very thin, very well-controlled layer. But the positive news is that basically it looks like an MRAM system for some, and we have all capabilities to develop these TMR sensors in 300mm fab because we have all the MRAM development tools required. So we've got Canon and ELVA for as a PVD cluster. We've got TEL-MSL for ionization under controlled magnetic field. We have Canon and ELVA for oxidation and encapsulation. And we've got also KLA measurements setups for in-plane and out-of-plane magnetic field sensing to calibrate what we produce. So basically, currently, we're developing TMR for several partners that we might want to expand if you have interest in that field. And that brings me to the last of the last topics for today, and that's the one of quantum magnetometry using nitrogen vacancy diamond color centers. I told you about diamond being a very nice power material, but difficult to handle, but it's also a brilliant material for thermal dissipation, but also for magnetometry. Because diamond is a form of solid-state vacuum. It's a very inert crystal, very low chemical reaction, very, very robust, very strong. But if you kick out 2 carbon atoms from that material, you have 2 vacancies. And if you replace one by a nitrogen atom, you create a quasi-particle which is fixed in the crystal under one of 4 directions, which is fixed by the crystal of diamond. And that object has fluorescence characteristics that are depending on the energy level occupation in the material. And these energy levels are dependent on a magnetic field applied in the direction of that quasi-particle because of the Zeeman splitting appearing in the energy level of that quasi-particle. If you can access these splitting measurement, you can know the amplitude of the field in the direction of that quasi-particle, And you can do that in 4 directions, so that you can obtain then the three-dimensional direction of the magnetic field as well as its amplitude. And because you've got 4 measurements, you can also retrieve the temperature with high resolution in that system. And the graph on the left shows you that you can have at room temperature the performance of cryogenic squid otherwise with very compact form factor. So this is the reason why we do these developments, and we do that currently by growing diamonds on our side, including these NV centers, and we are also flying some of these magnetometers in space. Some of those went to ISS for demonstration, and we are currently moving these diamond films on top of our wafers for quantum networking and quantum sensing by integration on the photonic platform that is very mature and that we use to diversify the output beyond datacom and telecom. I'm out of time, so I will very quickly thank you and open for questions if you have some.
Now it's open for discussion. Any questions? Please.
Thank you for your very nice sharing. I just wonder, for the last slide, you introduced some possibility to use diamonds for the quantum application. So I wonder, for this activity in the imec, already in the research or development, or still in the pretty early phase?
So it is in research at this point in time, but what we are researching is the basic step towards quantum sensing that are the same steps we might want to implement for thermal management and for power device development. So we are currently focusing on the bonding of diamond and shearing to release thin foils of diamond locally that can be used for quantum sensing, for thermal dissipation, but also eventually for power devices if you want.
And then wondering, for this diamond material, are you going to use crystal diamond or CVD diamond, or yes?
So for best performance, we focus on quantum because quantum gives you exquisite performance target. If you manage it there, you'll manage it for the other ones. So for that, we need exquisite monocrystalline diamond. Okay. We have our own growth capabilities, but we are also partnering with procurement partners that are doing a business of producing these high-quality diamonds. Okay. They also produce lower-quality diamonds, which are very good enough for thermal management. And for power, we have to see what you need actually. But normally not quantum-grade diamond.
Okay, thank you.
I have one. You have like a lot of current sensing technologies, right? And is that possible to, integrate with your, for example, gallium nitride platform, like on-chip sensing, something like that?
So we strongly believe that integration with other features will be the way to go. We can definitely integrate on gallium nitride. The question is whether it's a right idea or not. That we don't know yet, because the complexity might make no sense at some point. So we think it could be compatible, but does it make sense to do? That's the question we're having, let's say. So to have a full TMR process on top of gallium nitride might not be a good reason to do. And integrating diamonds might be a good idea, because the diamond we integrate will be anyway in small islands of diamonds, so that we can repopulate a wafer with just on selected spot an island of diamond for local sensing, for example. But then we need to probably have photonic access over the full wafer. And then the question is whether we can reuse the photonics for other type of applications.